Good afternoon, guys. We're going to be looking at the questions from a Pure Math Unit 2 mock IA, or we can even call it a Pure Math Unit 2 worksheet from Module 1. Alright, without further ado, we get right into the questions. So the first question says, given that z is equal to I into 1 minus I into 2 plus I, show that z may be expressed in the form k plus 3i, where k is an integer. Now, all we need to do right here is really to expand this bracket and simplify. All right, so this is what we're going to be doing. So we have I into 1 minus I into 2 plus I. Now, of course, you have the option of multiplying any two expressions at first. So we could probably multiply the second two. So I'm going to have I, make this bracket bigger. 1 times 2 is 2. 1 times I is I. Minus I times 2 is minus 2i. And then, of course, minus I times I is minus I squared. All right. So I'm going to have I multiplied by 2. Now, I minus 2i would give me a minus I. And then I squared is negative 1. So I'm going to end up with a positive 1. This becomes I into combining the real parts, which is 2 and 1, 3 minus I. All right. So we're going to end up with 3i minus I squared. All right. But as we say, I squared is negative 1. So you're going to have 3i plus 1. Now we want it in the form k plus 3i. So we're going to turn it around and say 1 plus 3i. All right. And that would be it for the first part. Now moving to part 2 of the question, it says, hence find the values of the integers m and n, where 2 minus I, and you have the conjugate here. The smaller story means a conjugate, right? So you have 2 minus I conjugate minus m times z is equal to n into 1 plus 4i. Now the concept of the equality of complex numbers is that if two complex numbers are equal, the real parts are equal and the imaginary parts are equal. So let's go right ahead and populate the question. The conjugate of 2 minus I would be 2 plus I. So minus m times z. Of course, we're going to be using the simplified form of z, which is 1 plus 3i. So I'm going to have open bracket 1 plus 3i. And this is equal to n into 1 plus 4i. All right. Now let's see what happens. We need to expand and group the real parts and the imaginary parts. So we have 2 plus I minus m. Of course, minus m times 3i would be minus 3mi. And this is equal to n plus 4ni. All right, let's get some space here now. Now, if we were to group the real parts, here on the left, it would be 2 minus m. All right, putting the imaginary parts together. All right, we have I and we have minus 3mi. So what I can do is to have 1 minus 3m, and we'll put the I there. This is equal to n plus 4ni. Good. Now the real part on the left is 2 minus m. So we can say this implies that 2 minus m is equal to the real part on the right, which is n, and the imaginary part on the left, which is 1 minus 3m, is equal to the imaginary part on the right, which is 4m. Oh, not 4m, rather 4n. Good. Now, call this equation 1 and call this equation 2. The beauty about this is that you already have n as a subject of the formula, so you can simply sub equation 1 in equation 2. So sub equation 1 in equation 2. All right. So where we have n, we're going to be putting 2 minus 3m. So let's see what is going to happen. So this implies that we're going to have 1 minus 3m is equal to 4, open bracket, 2 minus m. So this is 1 minus 3m is equal to 8 minus 4m. All right, bringing all the m's to one side, we can say minus 3m plus 4m is equal to 8 minus 1. So this comes down to m is equal to 7. All right, so we have that worked out. Now we know that from equation 1, n is equal to 2 minus m. So n is equal to 2 minus 7. So n is equal to minus 5. And the question asks us to find m and n. So you can say therefore m is 7. And of course n is equal to minus 5. All right? And that would be the end of the question there. All right, we now move on to part B of the question that says represent the following locus on an Argand diagram. And we have z minus 2 minus I is equal to 3. Now, in the general form, we can actually recognize this because normally when we have z minus c equal r, we know it's a circle with center c and radius r. Good. So we need to have it in the form z minus c. So I'm going to write it as a modulus of z. We factor out the minus. We're going to have 2 plus I. And this is equal to 3. All right. So I know that the center of the circle is 2, 1. And the radius is equal to 3 units. So we need a circle with the center 2, 1. And then of course the radius being 3 units. So on your Argand diagram, so you draw a little Argand diagram. All right, please remember to label your axis. So you have MZ, so 1, 2 is going to be out here. So I'm going to need probably a bit more on my y-axis. So let me say I go by 2. So we have 2, 4, 6, 8, negative 2, negative 4, negative 6, negative 8. So we have MZ. All right, remember the y-axis would be like an imaginary axis. And then you're going to have RZ. All right, so even though it's a sketch, there are certain things that it's important to put on. So RZ. Okay, let me say I go by 1 here. So 1, 2, 3, 4. Try to get the numbers as evenly spaced as possible. Negative 1, negative 2, negative 3, negative 4. Okay, so let me put in the center. The center is at 2, 1. So 2, 1 is about here. Now, because the radius is 3, what you can do is go 3 units in different direction. So if I go 2 plus 3, so this will actually go up to 5, right? So I'm going to need some more space here. So let's say we'll put 5 there. This is going to go to 5, going upward. So as we're going to go up to 5, going downward, 2 minus 3 is negative 1. It's going to come down here. All right, so I should have had this a bit more space. If I go to the left, I'm also going to go to negative 1. So when you sketch a circle, and of course it's going to look a bit better than mine because I'm actually using, also getting this up perfect here. But you get the idea. Your circle should look much better, look much more like a circle. Now let me see if I can fix this up a bit. All right, so try to space the numbers evenly. You get a better circle out of it. So probably I want to put in the center here as 2, 1, and my radius is 3 units, right? So that would be part B. Now we move on to part C. Now part C says express 1 plus I root 3 and 1 minus I root 3 in polar form. All right, so if I'm going to put them in polar form, first thing I need is a modulus and the argument for each. So I'm going to call Z1 equal 1 plus I root 3. And I'm going to say Z2 is equal to 1 minus I root 3. Now let's start with Z1. Modulus of Z1 is equal to the square root 1 squared plus root 3 squared. All right, if you put all that inside of your calculator, you're going to end up with 2. Now, to get the argument, we want to have a little Argand diagram. Alright, so you have the imaginary part and you have the real part. Now, the thing about this is that the imaginary part is positive and the real part is positive. So when you have theta here, on the x-axis, you know, that's 1, on the y-axis, that's root 3. Alright, so theta is simply just going to be tan inverse of root 3 over 1. You can't just root 3. Theta is simply equal to, now you have two options. You can put this inside your calculator, or you can draw your triangle. Now when you tan inverse root 3, you're going to end up with pi over 3. On my second scenario, we can actually look at it and deduce the modulus of Z2, right? The signs doesn't affect the modulus. So we can also state that the modulus of Z2 is equal to 2, right? Because it has the same magnitude, and the magnitude is what will affect the modulus. So this minus sign has no bearing. Now, when we put this on an Argand diagram, so let me say imaginary axis, the real axis. 1 minus root 3. 1 is positive, minus root 3, that's going to be negative, so it's going to fall down here. Alright, theta. We can also deduce the argument as well, because guess what? If we were to ignore the sign, what we'll end up with is still pi over 3. It's just that it's going the opposite direction, so it's going to be negative pi over 3. So these two angles are really the same. The difference is the direction. When you go anti-clockwise, or when you go clockwise, sorry, we normally indicate the angle with a minus sign. Right? When you go anti-clockwise, it's normally indicated with a positive sign. So this would be really negative pi over 3. Alright, so in polar form, we can say that Z1 is equal to R, let me just do the general form, R into cos theta plus I sine theta. So Z1 would be equal to R, which is 2, open bracket, cos pi over 3 plus I sine pi over 3. For Z2, and I'm going to change the bracket here because I need to put the negative in a bracket so we don't get a wrong impression. So this is going to be cos minus pi over 3 plus I sine, open bracket, minus pi over 3. So we have both of them in polar form. Normally when you give you this as part of a question, there's normally a follow-up question, alright? Alright, second part 2, C says that hence prove that 1 plus I root 3 all raised to the 9th plus 1 minus I root 3 all raised to the 9th is equal to negative 2 to the 10. Now, what do I do in a case like this? We're going to be applying the Marv theorem. But if I'm going to apply the Marv theorem, I'm going to have to use a polar form. Because the Marv theorem says that if we have it in the polar form, Z is equal to R into cos theta plus I sine theta. Then this implies that if we have Z to the n, it's going to give me R to the n cos n theta plus I sine n theta. Alright? So when looking at this, in polar form, we know the polar form for each of these, right? We know 1 plus 3i, we just found it. So this would actually be, well, let me go ahead and say that 1 plus I root 3 is equivalent to 2 into cos pi over 3 plus I sine pi over 3. And then 1 minus I root 3 is equivalent to 2 also into cos minus pi over 3 plus I sine minus pi over 3. Alright, so putting all this together, what am I going to get? I'm going to have 2 open bracket cos pi over 3 plus I sine pi over 3. All of this will be raised to the 9th power. Similarly, this is added to 1 plus I root 3 raised to the 9th. So you're also going to have open brackets. I'm going to have 2 into cos minus pi over 3 plus I sine minus pi over 3 all raised to the 9th power. Alright, now this is where we bring in the Morph's theorem. So you're going to have 2 to the 9 cos 10 pi over 3 plus I sine 10 pi over 3. Good. Plus 2 to the 9 again into cos minus 10 pi over 3 plus I sine minus 10 pi over 3. Alright, all we need to do is to plug this inside our calculator. So when we plug in the cos of 10 pi over 3, alright, this should be 9 pi over 3, not 10, because the power here is 9. So my bad here. This would be 9. Okay, so let me put that in now. So it's going to be 9 pi minus 9 pi over 3 and minus 9 pi over 3. This really comes down to 9 pi over 3 pi really. So we're going to have to find a cosine of 3 pi, or we can just put it in as it is. Now, in bracket, I'm going to have 2 to the 9. So I'm just leave it as that, 2 to the 9. In bracket, this is going to give me negative 1, and this is going to give me 0, so that's out. So this is plus 2 to the 9. In bracket, I'm also going to get negative 1 plus 0, right? Now, what do you do here? You're going to have negative 2 to the 9 minus 2 to the 9. You have 2 of it. So you have negative 2 times 2 to the 9. So by laws of indices, you add the power, right? So you're going to have minus 2 to the 10 QED, because it was a proof question. All right, we'll move on to question 2. That says, for the function x greater than 0, the equation of a curve is y equal x multiplied by ln x all squared. Prove that the second derivative is equal to 2 over x into 1 plus ln x. Alright, so let's get right into it. We have y is equal to x ln x all squared. So we know we're going to have to introduce the product rule, the quotient rule at the same time. So my first derivative, which is dy dx, product rule says I differentiate the first function. When I differentiate x, I'm going to get 1. So it's going to be 1 times the second function, which is ln x all squared. Now, to differentiate ln x all squared, we're going to have to use a chain rule. So I'm going to bring the power to the front. Ln x will come back to a power 1, so I don't need to put it back in the bracket, multiplied by the differential of ln x, which is in the bracket, which is going to give me 1 over x, multiplied by the first function, which was x. And of course, all we need to do here now is tidy this up. So I'm going to have ln x all squared plus, of course, you can see that the x here cancels out the x here. All right, x into x is 1. So we have plus 2 ln x. That is my first derivative. My second derivative now is going to be d squared y over dx squared. Now, we have two pieces of function connected by the addition sign. I'm going to have to differentiate the first piece, which turns out to be a chain rule. So we bring the power to the front, we subtract 1 from the power, and then we multiply by the differential of the bracket, which is 1 over x. For my second function, I'm simply going to have 2 times the differential of ln x, which is 1 over x. So we can say this implies that d squared y over dx squared is equal to, we can see that the 2 over x is common, right? And the 2 is also, well, we can factor out the 2, we can factor out the 1 over x. So it becomes 2 over x, open bracket, you're going to have ln x plus 1. Alright, that's exactly what we wanted. So we go QED, that which has been proven. Let's go to the next question. Next question says, show that there is only one point of inflection. Find it. Now, the point of inflection occurs when the second derivative is equal to 0. So this is when d squared y over dx squared is equal to 0. Now, according to our information, d squared y over dx squared, so this would imply that 2 over x into ln x plus 1 is equal to 0. Now, the concept is that if two things multiply to give you 0, one of them must be 0. So I'm going to have 2 over x is equal to 0, or ln x plus 1 is equal to 0. Now, clearly that this cannot be solved, so this is not applicable. All right? This is going to give me ln x plus 1 equals 0. ln x is equal to negative 1. And of course, if ln x is equal to negative 1, we can change this to the exponential form, which is the base, which is e raised to negative 1 is equal to x. So x is equal to e raised to the minus 1. Alright? Now, we can say, therefore, so this would imply the function has only one turning point, because we have only one x value here. Alright, we need to find the corresponding y value. So we're going to say, recall, y was equal to x ln x all squared. So you're going to have y is equal to e to the minus 1 into, well, let me open the bracket, ln e to the minus 1 all squared. But what do we know about ln e? ln e is 1, so you're going to have e to the minus 1 times negative 1 squared. Negative 1 squared is 1, so you have e to the minus 1. Alright, so therefore, the point of inflection is the x value is e to the minus 1, the y value is e to the minus 1. Or you can go ahead and say 1 over e, 1 over e. Alright? We now move into the next question. This is an example of what we call a partial function. So the function z, which is written in terms of x and y, is equal to x ln y squared plus sine xy. Find dz over dx. So when I'm finding dz over dx, I'm going to be treating y like a constant. What do I mean by that? I'm going to treat y as if I were looking at 6 or 7 or 8. So I'm going to be differentiating the variable function and then putting back the constant if it is not attached to the variable. So let's go right ahead. So the partial derivative of z with respect to x means that I'm going to be treating y as a constant. So when looking at this function, the entire ln y squared is like 7. So you would ignore that. You simply differentiate x, which is going to give you 1, and the constant comes back. So you have ln of y squared. Similarly, you're going to be thinking of the y here as a constant. And what happens when you differentiate sine xy? We're going to differentiate the xy. When I differentiate x, I'm going to be left with a y. So that whatever the derivative is, it comes to the front. So you're going to have the y here. And of course, the differential of sine is cos. So you have cos xy. Similarly, when I find the partial derivative of z with respect to y, I'm going to be treating the x as a constant. So this x that is attached to the ln y squared, you're thinking of that x as a constant. It's not going to be affected. So you're going to differentiate the ln y squared. When I differentiate ln y squared, I'm going to end up with 2y over y squared. Good? The x will come back, so times x. Plus, when you differentiate sine xy, the partial derivative with respect to y, the x again is a constant. So you differentiate the xy, which means you differentiate the y term, which is going to leave you with x. So the x will come to the front. And of course, the derivative of sine is cos. So you have cos xy. Alright, and of course, you can tidy this up. So the y up here will take out one of the y's. So we're going to have 2x over y plus x cos xy. Alright, let's scroll this down. this says now that we should find the second partial derivative of z with respect to y, which means I'm going to have to find the derivative with respect to y partially of the same y function. So I'm going to have to differentiate this function down here again. Okay, now before we start differentiating it, let me write it back. So we have dz over dy is equal to, of course, in order to differentiate this, since I'm focusing on the y, this y is going to have to come up. So I'm going to have 2xy to the minus 1 plus x cos xy. So we want the second partial derivative of z with respect to y. Okay? It should be dy squared. So remember again, you're focusing on y, so you're ignoring the x. Alright, so what I'm going to have here is that this minus 1 is going to come to the front because I'm focusing on the y variable. So I'm going to have minus 2 xy, and you subtract 1 from the variable, so that's minus 2. Good. Now, we're not using a product rule here, of course, because the variable here is y. X is being treated like a constant, like 6, so you can ignore it. Alright, so we're going to differentiate xy with respect to y. When we differentiate xy, the differential of y is 1. We're going to be left with x, so the x will come to the front. So since we have x around here already, we're going to have x squared. Now, of course, the differential of cos y is negative sine, and we'll put by the xy. Now, of course, we can tidy this up, so this will be negative 2x. We can put it over y squared. Alright, well, I'm not going to put a plus because this is going to be negative, so it's going to be negative x squared sine of xy. We'll finish with that one. Now, how do we interpret this one? D squared z over dx dy. What this really means is the second partial derivative. Let me get the symbol correct. Alright, let me not write it like that. Let me rewrite it. This is saying the same thing as partial derivative with respect to x of the partial derivative of the first partial derivative with respect to y. So whatever you got for dz over dy, you're going to differentiate that with respect to x. Good. So once again, it's the same function here. Alright, so we're going to take the same function and differentiate it with respect to x. Alright, so this is going to imply partial derivative with respect to x. Let me put by the function there of 2xy to the minus 1 plus x cos xy. Let me just bring this up and get some space here. Alright, bear in mind you're focusing on the x variable, which means you're treating everything else as a constant. When you differentiate this x, you're going to get 1. So all you're going to have is 2y to the minus 1. Plus, here, we're going to have to use a product rule because the x variable occurs in both functions. So when you differentiate the first x, you're going to get 1 times the second function, which is cos xy. Plus, now we differentiate the second function, so we differentiate the xy with respect to x, which is simply just going to leave us with y. So we're going to have y there. The differential of cos is negative sine, so let me put in my bracket negative sine xy. Of course, all we have to do now is tidy up. So we have 2 over y plus cos xy. Alright, this is going to give me negative y sine xy. There are no like terms, so this is what we end up getting. Hello guys, we now move to the next question. It says Samantha is responsible for designing a catchment system whose volume can be modeled by the equation volume is equal to this, where x is in centimeters. Use the trapezium rule with 5 ordinates to estimate the amount of liquid the system can hold. Alright, so the first thing I want to do is that since we're using the trapezium rule, we want to give you a general idea of where this is coming from, right? So we're going to sketch a curve between the interval 1 and 2. So I'm going to have 1 here, I'm going to have 2 here. The curve is going to look something like this. Now, let's see what happens. Now, what I'm going to do is to divide the area on this curve into trapezium, basically. Even though this is modeling the volume, The trapezium rule really gives you the area underneath the curve, but that area would actually be equal to the volume, as you can see right here. So we're going to start and close this. So close that at 2. Now, in order to get trapeziums out of this, we're going to need to divide this into strips. Alright, so we're going to be divided, it says, using 5 ordinates. Ordinates are the lines that you have, which means we're going to have 4 strips. So I'm going to divide this into 4 equal parts. So 1. Call it 4 equal parts because the distance is here. Our base is here, would be the same distance. So this would be h, 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 h. Now, what we want to know is what is going to be at each interval. Alright, the boundaries are from 1 to 2. That's easy to decide. We say that h would be b minus a over n. N is the number of strips. Now, the number of ordinates will always be 1 more than the number of strips. So we have 4 strips, 5 ordinates. N is the number of strips. So the upper boundary is 2, the lower boundary is 1. The number of strips is 4. So h is equal to 0.25, or we say a quarter. So it means that here would be 0.25, 0.25, right, going out right across. Now these would form individual trapeziums, so we need to complete the top to get the trapeziums. Now because the curve is concave, the trapeziums would fall slightly above the curve, so it's going to be slightly more than the actual area underneath the curve. Good. Normally we'd work the trapeziums individual and then combine them, but when we combine them, this is the formula that we're going to get out of it. So area would be equal to half h. Alright, the first ordinate and the last ordinate will only be used once. So let me label the ordinates. This is y0, y1, y2, y3, y4. I will call them so because they are y values. So here I'm going to have the first and the last one will just be y0 plus y4, right? Those don't repeat. Plus 2 times the other ordinates. So we have y1 plus y2 plus y3. We simply just need to draw a table for this. So you're going to have your x values, your y values. Now, of course, my first x value is always going to be the lower boundary, which is 1. And we keep adding the h as we go along. So we have 1 plus 0.25, 1.25. At 0.25 to that, we have 1.5. At 0.25, we have 1.75. And at 0.25, we have 2. So let's count 1, 2, 3, 4, 5 ordinates. Now, to get the y value, we simply use a function. So we're going to plug 1 into this function here in the place of x. So you're going to have ln1 is 0 squared times y. So this is really going to be 0. Alright. Now let me show you what comes out of this. This is your y0. This is your y1, y2, y3, and y4. So using a calculator, you're going to plug the rest of values inside of your function and round off to the required number of decimal places. So we use a calculator to populate the table. Now we simply just need to go back to the formula and say area is equal to, alright, this is going to give me a half. My h value is 0.25 into y0 plus y4. So y0 is 0, y4 is 2.178. So 0 plus 2.178 plus 2 times everything else. So 2 times 0.701 plus 1.274 plus 1.758. And of course, all this can be plugged into your calculator at once. So my area would be, plugging all this inside, this comes down to 1.206. Alright, now let's go back. Bear in mind that this was reflecting the volume. So therefore, we're going to say that the volume of concrete required to make or to design the model would be equal to 1.206 cubic centimeters. That will be the end of this particular question. Alright, moving to question B. It says, given that f of x is equal to 3x squared minus x over x minus 1 to x squared plus 1. Express f of x in partial fraction. So the first thing I need to check is to ensure that this function is not improper. It's not improper because the highest power of the variable in the denominator, if I were to expand, would be x cubed, right? So we're going to have 3x squared minus x all over x minus 1 times x squared plus 1. Now, we have two things here. We have a linear factor and we have a reducible quadratic factor. So this would be equivalent to a over x minus 1 plus bx plus c over x squared plus 1. Alright? So multiplying out by the LCM, this means that 3x squared minus x would be equal to a times x squared plus 1 plus bx plus c, sure I put that in a bracket, times x minus 1. Now we can start by letting x equal to 1. Because this would cancel out. So I'm going to have 3 times 1 squared minus 1. All of this would cancel out. So I'm just going to have a times 1 squared plus 1. So we have 2 is equal to 2a, which implies that a is equal to 1. Now, to find the other factors, since we can't make any more substitution, we can move on to comparison. So you could expand the brackets completely. So we have 3x squared minus x equal to a x squared plus a plus b x squared minus bx plus cx minus c. Alright, we'll start by comparing the highest power on the variable, which is x squared. So you're going to have the coefficient of x on the left is 3. On the right, it's going to be a plus b. But we know that a is 1. So you're going to have 3 equal 1 plus b, which means that b is equal to 2. Alright, we now move to the second highest, which is the coefficient of x. On the left, we can clearly see that it's negative 1. And on the right, we can see that the coefficient of x is negative b and positive c. So we have negative 1 equal negative b. Since b is 2, we're going to have negative 2 plus c. So we're going to have negative 1 plus 2 equals c. So c is equal to 1. So in partial fraction, this becomes a, which is 1 over x minus 1 plus bx. So I'm going to have plus 2x plus c all over x squared plus 1. Alright, so that is it in partial fractions. This says hence integrate f of x, right? So we know that's we're going to be using the partial fraction version. So the integral of f of x dx is equivalent to the integral of 1 over x minus 1 plus 2x plus 1 all over x squared plus 1 dx. Now whenever we have an integral connected by addition or subtraction, we can split it. So we have the integral of 1 over x minus 1 dx plus the integral of 2x plus 1 over x squared plus 1 dx. Alright, now for the first part, clearly we can see that the numerator is the differential of the denominator, and in that case, it simply becomes ln x minus 1. In this case, if you differentiate the denominator, you're going to get 2x. So the 1 is going to be a problem. So what I can do is to split that. So the integral of 2x over x squared plus 1 dx plus the integral of 1 all over x squared plus 1 dx. Clearly we can see that this is a ln function. We're looking at this here, 1 over x squared plus 1. This should remind us of tan inverse x. So this becomes ln x minus 1 plus ln x squared plus 1 plus tan inverse x plus your constant of integration. Don't forget that. The ln functions can be broken down further, right? So you could put this over this or multiply this by this. You could go ahead and do that. Alright. Now, once you have done that, that would be the end of this question. Let me just put it in there. So it's ln of x minus 1 times x squared plus 1, right? So write that as a single function, plus tan inverse x plus c. We now move on to question C. And in question C it says, well, C part 1, use the substitution x equals sine squared theta to show that the integral of all of this is equal to that. Now, one of the things I want to talk about is that whenever you have boundaries and you're doing substitution, like in this case, the function is in terms of x. So these are x boundaries. All right, we're going to be changing it in terms of theta. So we're going to want some theta boundaries. So let me go ahead and start by saying that x is equal to sine squared theta. All right, as we said, these are x boundaries. What we want is theta boundaries because we're going to change the function out in terms of theta. So I'm going to transpose a theta here. So we can start by square rooting both sides, right? So if x is equal to that, square root of that. So we can say that root x is equal to sine theta. So we can say theta is equal to sine inverse root x. All right, so we can say when x equal 1, because that's an x boundary, theta is equal to sine inverse square root of 1. The square root of 1 is 1, so it's really sine inverse 1. Sine inverse 1 is pi over 2. Also, when x is equal to 0, theta is equal to sine inverse square root of 0. And of course, you know that the square root of 0 is 0, sine inverse 0 is 0. So theta is equal to 0. All right, let us fix up the other things. The next thing we need to talk about is the dx. If we're changing it in terms of theta, we need to have d theta. So it's that x is equal to sine squared theta. We can find dx over d theta. And we're going to have to apply the chain rule here. So we bring the power to the front. So it's 2 sine theta to the power of 1. We don't need to put the 1 there. And then, of course, we multiply by the differential of sine theta, which is equal to cos theta. Now, right away, by just looking at this, this is actually an identity. Right? 2 sine theta cos theta. But let me leave it as that for now. We can say that dx is equal to 2 sine theta dx, 2 sine theta cos theta d theta. Now we can go ahead and make the substitution. So we know the boundaries will now be 0 and pi over 2. In the place of x, we're going to be putting sine squared theta. So I'm going to have 1 minus sine squared theta over sine squared theta times where you have the d theta, or the dx, sorry, where you have a dx here, we're going to replace that with 2 sine theta cos theta d theta. So 2 sine theta cos theta d theta. All right, let me pull this over so I can have some more space. All right, what are some of the things that we can use to simplify here? We know that 1 minus sine squared theta is cos squared theta. So this becomes the integral of the square root of cos squared theta over sine squared theta times 2 sine theta cos theta d theta. Now somebody might say that cos squared theta over sine squared theta is cot squared theta, but that is not inside of your answer. As you can see, it's a proof question, so I don't want to do that. All right, don't leave off your boundaries that are 0 and pi over 2. All right, next, what is going to happen is that when I square root cos squared theta over sine squared theta, the square root of that will be cos theta over sine theta. All right, this 2 that is right here can go outside the integral, but then again, we don't need to put it out there because if you look here as well, it is inside. So let me say multiplied by 2 sine theta cos theta d theta. All right, let us see a few things that can happen here. Sine theta takes out the sine theta here. So this becomes the integral between 0 and pi over 2. Alright, so you have cos theta times 2 cos theta, which is going to be 2 cos squared theta d theta. Is that what we wanted? That's exactly what we wanted. So we say Q E D. Alright, so we have to work that out. Alright, second part of the question says, hence evaluate this. So the first thing I need to state is that all this would have proven that this would have been equivalent to the integral between 0 and pi over 2 of 2 cos squared theta d theta. Right? Would have proven this. So in order to integrate this, we just need to integrate this one here. So this becomes, we can put the 2 outside, the integral between 0 and pi over 2 of cos squared theta d theta. Now here's my problem. My problem is the power that the cos has. So we're going to have to find a way to rewrite cos squared theta without having that power up there. But how do we do that? The double angle formula. So we know that cos 2 theta is equivalent to 2 cos squared theta minus 1. So we simply just need to transpose this for cos squared theta. So we can say cos 2 theta plus 1 is equal to 2 cos squared theta. So we can say cos 2 theta plus 1 all over 2 is equivalent to cos squared theta. Alright? So this becomes integral to outside, replacing the cos squared theta with cos 2 theta plus 1 over 2 d theta between 0 and pi over 2. But as you can see here, this 2 takes out that 2. So it becomes the integral between 0 and pi over 2 of cos 2 theta plus 1 d theta. Alright? Now when I integrate cos 2 theta, I'm going to end up with sine 2 theta over 2. And when I integrate 1, I'm going to end up with theta. The boundaries are 0 and pi over 2. Good. So we input the upper boundary. So I'm going to have sine 2 times pi over 2 all over 2 plus pi over 2 minus, when I put in the lower boundary, which is 0. So I'm going to have sine 2 times 0 over 2 plus 0. Alright, of course we know that sine 0 is 0. So all this over here is 0. Now let's see what happens here. I'm going to end up with the sine of pi over 2 plus pi over 2. Now when I sine pi, I'm going to end up with, so we're going to have 0 over 2 plus pi over 2. So really the answer here is simply just pi over 2. And we can write a final statement that says, therefore the integral of this is simply equal to pi over 2.